Inside tissue, immune defense is a physical process. A macrophage detects an invading pathogen, extends its membrane, and engulfs the cluster to break it down. To a biologist, this is phagocytosis. To an applied mathematician, it is a dynamic system governed by replication rates, fluctuating molecular concentrations, and spatial decay. Consider an infection by the gram-positive bacterium Staphylococcus aureus. The presence of this specific pathogen triggers an interconnected cascade, activating both the fast-acting innate immune cells and the long-term adaptive immune response. Clinical immunology typically describes these interactions through observation. Physicians know which cells respond, but predicting the exact timing and magnitude of that response through math has remained a significant hurdle. Building a computable model of this system requires tracking two distinct processes at once: the physical movement of the cells and the continuous chemical signaling between them. Translating the human immune response into a mixed cellular cytokine model provides the structural framework necessary to simulate how a disease will progress. A single unified equation format cannot capture the immune system because its components exhibit distinct physical behaviors. The cellular agents, the invading bacteria and the defending macrophages, are distinct physical bodies. They occupy volume and actively migrate through three-dimensional tissue and spatial diffusion over time requires partial differential equations, or PDEs. The chemical signaling agents, known as cytokines, behave differently. They exist as localized concentration levels that spike and dissipate within the tissue, rather than physically migrating across it. To model these temporal fluctuations in localized concentration, the system relies on ordinary differential equations, or ODEs. These two mathematical models must continuously interact. The PDEs dictate where the cells are physically located, and those locations dictate where the ODEs calculate the localized release of chemicals. Separating spatial cell dynamics from temporal chemical signals creates a solvable architecture for human immunity. This diagram maps the biological agents of our mixed cellular cytokine simulation to specific variables. On the left, the S. aureus pathogen is defined as Y1. The innate response begins with resting macrophages, mapped as Y2. Once engaged, they transition into activated macrophages, Y3. Within the partial differential equations, biological decay is represented by the term negative mu times Y. This calculates the natural death rate of a cell, independent of the immune system. Phagocytosis, the actual destruction of the pathogen by the macrophage, is quantified by the interaction term negative lambda 2, Y1, Y2. Cellular migration is treated as a mathematical diffusion process, governed by the Laplacian operator delta, scaled by a specific diffusion coefficient. Setting these PDE parameters establishes the physical cellular baseline. Once the cells are in position, the chemical signaling cascade begins. As the macrophages activate, they secrete a network of communicating cytokines, specifically tumor necrosis factor alpha, interleukin 6, interleukin 8, and interleukin 10. This formula is equation 6, the ODE governing the concentration of interleukin 6. The central term illustrates how the model handles biological feedback. Parameters K8 and K9 define basal rates where activated macrophages upregulate production of the cytokine. The variables marked with an H are sigmoidoidal functions. The model uses these to translate biological signaling into mathematical quantification. The upregulation term, HCU, calculates how TNF-alpha mathematically triggers an increase in interleukin 6 production. Simultaneously, the downregulation term, HCD, calculates the suppressive effect of interleukin 10, an anti-inflammatory cytokine. The equation also includes an auto-negative feedback loop, meaning interleukin 6 actively downregulates its own production over time. Biologically, this mathematical tension is the mechanism that prevents a lethal cytokine storm from destroying host tissue. The exact point at which a cytokine reaches peak influence in this equation is dictated by the half-maximum value parameter, denoted by eta. By utilizing Hill functions, the simulation translates biological homeostasis into self-regulating mathematical boundaries. Because the system is nonlinear and coupled, exact analytical solutions are impossible to calculate. Standard statistical regression models are insufficient here, as they cannot map the continuous, time-dependent biological feedback loops within the system. Solving the model requires a discrete numerical technique, the explicit predictor-corrector scheme. This visual timeline shows the technique in action. The solver integrates the equations over an extremely small interval, moving from current time tk to a half step at tk plus 1/2. Continuous equations are converted into discrete steps using Taylor series expansions. The mathematical error term is truncated to the order of sigma cubed, which balances high computational precision with practical processing speed. This is the predictor phase. Using forward difference formulations, the algorithm estimates the system's future biological state at the half step. Relying solely on this predicted value is inaccurate. In nonlinear biological systems, a small predictive deviation rapidly leads to massive compounding errors. To fix this, the algorithm introduces the corrector equation. It takes the estimated half-step value and feeds it back into the initial function. The corrector refines the initial calculation, yielding a stable value at the full step tk plus 1. This two-step loop architecture allows the simulation to step forward in time continuously without mathematical instability. To perfectly balance the algorithm, specific scalar adjustments are applied during the derivation, setting C1 to 3/2 and C2 to 1/2. These constants ensure the completed scheme is both zero-stable, meaning errors do not grow exponentially, and second-order accurate. With the solver built, researchers can input raw clinical data, such as a localized, low-concentration dose of Staphylococcus aureus, directly into the model. This graph represents the output. As the data processes through the predictor-predictor mock, the algorithm calculates a dynamic, measurable clinical projection. The resulting time series accurately predicts the specific spikes and decays of individual cytokine concentrations in response to the bacterial load. This specific second-order architecture processes these nonlinear equations with higher efficiency than the standard iterative schemes often used for coupled systems. The model's value lies in predicting ex vivo and in vivo experimental data, providing a computational bridge between cell activation and cytokine expression. By pairing rigorous numerical solvers with mixed cellular cytokine models, the dynamic of an infection becomes a solvable system of equations.